Okay, so today we're going to be talking about trade-offs, in particular accuracy and interpretability versus bias and variance. And so these are kind of two sides of the scale. You want to make sure that you're doing an accurate analysis, but you also want it to be interpretable. And then this bias-variance trade-off, this might be something you've heard before. This is really the crux of statistics. A lot of what we're doing is really balancing between bias and variance, and it's going to come up a lot in this class. And so this definitely won't be the last time that you see it. So let's get into it. All right, so as I mentioned in the last class, there are two kind of main categories of analyses that we're going to be talking about. There's regression and classification. And so regression is when you have a quantitative response. And so that's like a numeric response. Something like blood pressure would be a quantitative response. Classification is when you have a qualitative or a categorical response. And so this could be something binary, like yes or no, or it could be something with more categories. For example, in the slides from the first day, we talked about zip codes as something you could want to classify the numbers from zip codes, and each of those numbers could be a different category, and so that would be a classification problem. So that was an example of a regression problem, something like trying to predict blood pressure, or there's kind of numerous different things that you could try to do with a regression problem. Anything where you have a quantitative response. And then, as I mentioned, that zip code example is a classic classification problem. So this first set of slides, we're going to be talking specifically about regression. So here's an example. I've got some auto data. And so here I have miles per gallon on the y-axis on all three of these plots. And on the x-axis, I have horsepower, weight, and acceleration. And so the dots represent data points for each of these, where along the x-axis, where we've got a predictor, either horsepower, weight, or acceleration. And on the y-axis, we have our outcome of interest, miles per gallon. And so this is a regression problem because miles per gallon, our y variable, our outcome variable, is continuous, it's quantitative, it's something that has kind of multiple continuous values within some range rather than categories. So these blue lines that I've drawn on each of these are the linear regression line that fit separately to each of these x variables, horsepower, weight, and acceleration. And so the question is, can we predict miles per gallon using these three variables? And so maybe we could be doing better using some model that looked at these all together rather than separately. So in each of these plots, I'm just using one variable at a time to predict miles per gallon. And you could imagine that instead of doing that, I could have some function of these three variables together, some function of horsepower, weight, and acceleration, and that could try to approximate our miles per gallon. So miles per gallon, again, is the response variable here. It's that outcome variable, the thing that we refer to as y. I'm going to be doing these notation pauses kind of throughout this lecture and the first couple sets of lectures just to make sure that we're all on the same page, because sometimes notation can differ between classes. A great place to post questions about notation is in our discussion forum. I'm happy to clarify any of these kind of as we go through. So horsepower, for example, this is a feature, an input, or a predictor. And we refer to this as x1. And then weight is also a feature, input, or predictor. I'm going to call this x2. And acceleration, also a feature, input, or predictor. I'm calling that x3. And so our input vector, this is our vector of x values, our vector of features, looks like this. It's x equals x1, x2, x3. And our model is y, which is miles per gallon, equals f of x, so some function of x, some function of this input vector, plus epsilon, our error. So why do we care about f of x? Well, we can use this function of x to make predictions of y for new values of x. So for example, if I had a new car and I found out the acceleration of the car along with the other x variables in my model, I could predict the miles per gallon for that car without having to calculate it myself. Another use case would be maybe I just want to gain a better understanding of which components, x1, x2, all the way up to xp, are important for explaining y. And so in this case, I have x1, 2, and 3, and maybe I'm interested in knowing, hey, is one of these more or less important for explaining miles per gallon compared to the others? And depending on how complex this function f is, maybe we can understand how each component xj of x affects y. So how do we choose this f of x or this function of x? What would a good value of f of x be at any selected value of x? So for example, at x equals 100, there could be many values of y at that. How would I maybe pick something that would be sensible if I just wanted to estimate when horsepower is 100, if I wanted to estimate what the miles per gallon would be, what might I do? Well, this plot kind of gives you a little indication of what I think a sensible thing might be, but a good value would be potentially plugging in the expectation, which this is the same thing as the average. And so the function of 100, or the function of x here, would be the expected value of y given x equals 100. And so the expected value, or the average of y given that x equals 100, or given that horsepower is 100, and this is called a regression function. This ideal f of x, this expected value of y given x, that's the regression function. So this actually also works over a vector of x. For example, instead of just having the expected value of y given x equals x, I could have the expected value given x1 equals little x1, x2 equals little x2, and x3 equals little x3. So this is the optimal predictor of y in terms of mean squared prediction error. We're not going to fully get into why this is optimal, although if it's something that you're interested in, this semester I'm also teaching a linear models class where we get into kind of more of the nitty-gritty as to why this is optimal. And so if you take that class in the future, or maybe you're enrolled in it now, then you'll be able to get a little more insight into that. And so what do I mean by that it's optimal? I mean that this function, the expected value of y given x equals little x, or this regression function, it's the function that minimizes the expected value of y minus g of x squared given x equals little x over all functions of g at all points of x. So basically, it's going to minimize that squared error across all potential functions. So you could pick a whole bunch of different functions to try, and this one is going to end up with the smallest mean squared prediction error. And so the epsilon that we talked about before, that is y minus f of x, that's called the irreducible error. And even if we knew f of x, we would still make errors in prediction, since each x is typically a distribution of possible y values. So this is important to know that there's this irreducible error here, this epsilon, that even if we perfectly knew f, we would still end up with. Okay, so let's go back to this picture. So using these points, so I've got a couple of points that are right where x equals 100 in my data set. How would I calculate that regression function, that expectation of y given x? Well, the simplest way, and the way that you would do it in this single case, is you would just take the average. So the expected value of miles per gallon given horsepower equals 100 is going to be 19.6 in this case. So this point here at the top, this point has a y value of 32.9. What do you think the error is there, the epsilon for that given point? So you would take that y, that 32.9, and you would subtract what we would get with f of x. That was that 19.6. And you end up with 13.3. And so that's the error for that point. Sometimes we call this a residual. So the error for any given f hat, and so that's going to be a predicted, a estimated function of f, we have the reducible error and the irreducible error. assume for a moment that both f hat and x are fixed. The expectation of y minus y hat squared, this represents the average or the expected value of the squared difference between the predicted and the actual values of y. And then this variance of epsilon, that represents that irreducible error, that represents the variance associated with the error term. And so the focus of this class is going to be on techniques for estimating f, with the aim of minimizing this reducible error here. The irreducible error is always going to provide an upper bound on the accuracy of our prediction for y. And this bound is almost always unknown in practice. So typically we have very few, if any, data points at a given x equals x point exactly. And so we can't necessarily compute this average, this expectation of y given x equals x. For example, what if we were interested in estimating miles per gallon when horsepower was 104? In my data set, I didn't have any values there. And so instead of taking the exact expectation at a given x value, we can relax that definition and let our f hat here be the expectation of y given x in some neighborhood. So this nx is some neighborhood of x or some region around x. So let me just pause again for notation here, just to kind of make sure we're all on the same page. This E here, that means the expectation. When you see that it often means that we're taking basically some kind of average. And so this means we're taking the expectation, and then in brackets, the first thing is y. We're taking the expectation of y. This up and down bar means given. So we're taking the expectation of y given, and then x is in the neighborhood of x. And if at any point during this class you need a notation pause, please let me know. Again, as I mentioned, the discussion board is a great place to post questions about notation, and I'm happy to clarify any of this further. Okay, so we can relax this definition and let our f hat be the expectation of y given x is in some neighborhood of x. So nearest neighbor averaging does pretty well with small p, p being the number of predictors. So p less than or equal to 4 and large n. And so n being the number of observations when you have a lot of observations. Nearest neighbor is not great when p is large, and this is because of something known as the curse of dimensionality, because nearest neighbors tend to be far away in high dimensions. So what do I mean by p and what do I mean by n? A little more notation here, but p is basically, again, the predictors. N is the number of observations. So a common model, a parametric model, which is different from one of these nearest neighbor models, is a linear model. And this should look familiar from previous classes that you've taken. So here's another f of x that you could propose, where it has beta 0 plus beta 1 x1 plus beta 2 x2 all the way up to beta p xp. So you have p predictors here. A linear model has p plus 1 parameters, and that's because it has an intercept, beta 0. So you have the parameters beta 1 up to beta p for each of the p predictors, and then beta 0 for your intercept. And so you can estimate these parameters by fitting a model to training data. And although this model is almost never correct, it can often be a good interpretable approximation to the unknown true function of f of x. So let's look at a simulated example real quick. So here I am predicting income, so that's my y-axis here, from education and seniority. And so the red points in this plot are simulated values for income from this model. Income equals some function of education and seniority plus some error. And f here is the blue surface. And so the true underlying function is this blue surface, and the red are the actual simulated points that were simulated from that function. So here is an image of linear regression model fit to this simulated data. So in this case, my f hat, my estimated function of education and seniority, is beta 0 hat plus beta 1 hat education plus beta 2 hat seniority. And so instead of fitting something kind of close to each of these points in such a way that it sort of like wiggles between them, I'm fitting just a single plane through them, like a straight plane that goes through in this linear manner. I could alternatively fit a more flexible regression model, and so here I have a more flexible one, which I'm calling f hat sub s, to the simulated data. And so here I'm using a technique called a thin plate spline to fit a flexible surface. And here's an even more flexible version. So here I've basically drawn the surface to hit every single one of these red points. And so that's going to fully minimize the error, as in if I look at any of these single points and I try to calculate the error between my f, the function that I've chosen, and these points, that error is going to be 0. But I'm completely overfitting when I'm doing this. And so what you want to do is basically find a balance between that. And so the first type of balance that you're trying to find is between prediction accuracy versus interpretability. Linear models are very easy to interpret. Thin plate splines are not so much. And so you kind of want to strike the balance. And the other thing we're trying to strike a balance between is good fit versus overfit or underfit. We want to know basically when the fit is just right. And then we've got this idea of parsimony versus black box. And so we often refer to simpler models including fewer variables. We often prefer those to black box predictors involving all of them. And so a parsimonious model or a simple model that's easier to explain, this kind of goes under the prediction accuracy versus interpretability, kind of under that heading as well. And so these are some different types of models that we're going to be talking about in this class. And on the x-axis here, I've got flexibility from low to high. And on the y-axis, I have interpretability from low to high. And so this top here is a relatively, it's not as flexible of a model, subset selection and lasso, but these are highly interpretable. They're much easier for people to kind of understand. And I've got this little bit less interpretable, a little bit more flexibility, least squares. And then up here at the very top, we've got highly flexible models like bagging and boosting or support vector machines that have low interpretability. So accuracy, we fit a model f hat of x to some training data. And we can measure accuracy basically as the averaged square prediction error over that training data. So that training data is basically just a combination of x and y's, so x being the predictors, y being the outcomes across a set of values, a set of observations. And so this average squared prediction error or mean squared error of the training, this is basically one way to measure accuracy. But what can go wrong here? Well, this is the big idea of overfitting. So if we are measuring accuracy based on the training data, then we're going to end up, if we are optimizing this equation here, if we really want to minimize y minus f hat of x squared across the training data, and so that means the data that we're observing, well, the best way to do this is just to play connect the dots. So in that simulation I showed you, the mean squared error of the training data is going to be minimized. It'll actually be 0 in that third example where I just connected the dots between each of those red points. Now that was not the best, that model was not the closest to the true underlying f. Of the 3 models I showed, probably the thin plate spline was the closest to that original f. But if we are sort of optimizing for the wrong thing, we can end up kind of overfitting our model. So we want to be careful about what we're deeming as our measure of accuracy. So let's see this in a bit of a simpler example. I have some training data here that I've plotted. And what f hat of x would minimize this mean squared error of this training data? So I'm just going to give you a second to look at this and try to look at your screen and think about if you could come up with some f hat or some function that would minimize that mean squared error of the training data. Yeah, so connect the dots. This is going to make that mean squared error absolutely 0. If I just drew a line between each of these points, and then I fit this where I'm basically taking the observed y minus my predicted y squared. Well, my observed y and my predicted y here are exactly the same because I've just connected all these little dots along the way. But it's very unlikely that this is actually the true underlying function. This is certainly going to be an overfit model. If we get a new sample, so if I sampled again from that same f, the same underlying distribution, that overfit model is probably going to be terrible. So if I now tried to get the prediction accuracy for this very overfit jaggedy model, I'm not going to do well at all with new data. So instead of measuring accuracy as the average squared prediction error over the training data, we can actually compute it using some fresh test data. And so you'll notice the difference between this test data and this training data is this training data is going from 1 to n. So this is a sample from 1 to n. This test data is on a new sample. So this is a new set of observations from 1 to m. And so now, instead of measuring accuracy on the same data that I used to fit my model, I'm going to measure accuracy on a separate data set that comes from the same underlying distribution but wasn't used to fit my original model. And this is going to ensure that we're not overfitting, and this is a much more practical measure of accuracy. So the equation looks exactly the same, except that we're averaging over the test sample instead of over the training sample. So here's another image that sort of gets at this idea. So the black curve here is the truth on the left. So this black curve, that's the true f that we're trying to target. And this red curve on the right, this is the mean squared error in the testing. So the accuracy that that's our measure of accuracy that we've determined using the testing sample. And this gray curve here, that's the mean squared error using the training sample. And then we've got an orange, blue, and green square here on each of these curves, and those correspond to the orange, the blue, and the green curves. And so those correspond to basically different flexibilities. So this orange line here, the straight line, that is a linear model. And so in both cases, there's higher mean squared error for both the test data and the training data. This is our least flexible model. On the bottom here, on the x-axis, we're measuring flexibility. On the y-axis, we're measuring mean squared error. So for this very inflexible model, we've got a pretty high mean squared error for both our test data and our training data. The next is the blue line, which is kind of follows this curve. The blue actually does a pretty good job of estimating our black curve. It's almost hard to see because it's just behind it. And so that falls here. And so for that one's kind of in the middle flexibility-wise. And it's not perfect in the training data, and it's the best we can do in the testing data. Basically, it falls on the bottom of this curve of the testing data, which is where we really want to be because we want to be minimizing that mean squared error. And then this green, this is the last one here, this green wiggly line. In the training data, that's basically like playing connect the dots. And so we've really overfit to our training data. That has the maximum flexibility. So our mean squared error, if we were just looking at the training data, would look really good. But remember that that's really not the thing we want to be optimizing because that's just going to overfit to the data we have on hand. And what we often want to do is build models that can be used in the future. And so we really want to be using some outside data. And when we do that, when we use our testing data, you'll notice the mean squared error shoots up. So even though this is more flexible, it's farther off from our truth here, our true black line, our true f of x that we're trying to target. And so we kind of are trying to find this sweet spot, which happens to be right around the blue of that accuracy based on the testing data. So here the truth is smoother. So the smoother fit and the linear model do really well. And so this is kind of the same idea, but just with a different set of data. So the underlying truth, the underlying f of x is still this black line. And then I've got a straight line here. My linear model is orange. Blue is a little bit more flexible. And then my green is, again, very, very flexible. And so looking over here at my mean squared error plot, I see a very similar pattern, where here it looks like blue might be slightly better than orange, but both are pretty similar in terms of my test error, which is the error that we want to be focusing on. If we look at the training error, of course, as we get more flexible, that error is decreasing, but that's not really what we're interested in. We really want to be able to make sure we can have a good out-of-sample model, something that can work well on testing data that we haven't already seen. And as we get more flexible, again, we end up seeing that that error is going to increase in the testing data. Here, the truth is wiggly, but the noise is low, so more flexible fits do best. And so here we've got this black line here again, which is my truth. I've got a blue that kind of falls a little bit under that, and then I've also got my green that is not too far off from that either. And then I have my orange, which is my linear fit, which really doesn't fit this particular noisy model. And so here again in the gray, I have the mean squared error for my training data, and that is always going to decrease as our flexibility increases. So it's not really very informative. My red line, on the other hand, my mean squared error for the test data is much more informative. And in this particular case, blue still looks like it does slightly better, but green is really not so bad. And that's because this is a wiggly model. We've got this kind of curve, and we don't have a lot of noise. The points are pretty close to the truth. And so even though we're playing connect the dots a little bit, because there's not a lot of noise or a lot of deviation from that truth in these individual points, that green really doesn't end up overfitting so dramatically. So these are basically just 3 different examples of showing when we have kind of some like medium model, a more linear model, and a wigglier model, and how we can use the test error, this red line, to basically decide which model is going to be best for this. And often we're trying to find that sweet spot. So this is the bias variance trade-off. Basically, we fit some model f hat to the training data, and then we're going to pull a test observation from this population. So, for example, x0 and y0. The true model is y equals f of x plus epsilon. And so we're trying to kind of get at this, this f of x is the expectation of y given x. And we can show that basically this expectation of y0, so our test observation minus our fitted model on x0 squared, we can separate that out into the variance of f hat of x0 plus the bias squared plus the variance of epsilon. And so the expectation basically averages over the variability of y0 as well as the variability of the training data. And so as the flexibility of f hat increases, so as the flexibility of our model increases, which in those plots I was just showing on the previous slide is as we're moving to the right on the x-axis, so as that flexibility increases, the variance increases and the bias decreases. So choosing the flexibility based on the average test error amounts to basically this bias variance trade-off, where you're trying to find that sweet spot where you have not too much variance and just the right amount of bias, not too much bias. So these are 3 different plots of showing the mean squared error, the bias, and the variance across each of those examples that we just did. So the first example was one that kind of fell somewhere in the middle, and we had this kind of this test error here, the mean squared error in our test sample. The blue shows the bias, and the orange shows the variance. And this dotted line shows that sweet spot of flexibility. So we're trying to find basically right here where we're minimizing the variance and the bias simultaneously. This second example was our linear model. This is our less flexible model, so the truth was less flexible here. And so you'll see that this dotted line falls farther on the left, so in the less flexible region. Again, we've got our mean squared error here. The orange is our variance, the blue is our bias, and we're basically trying to minimize that. And then here we've got our third example, which was a highly flexible model that had not a lot of it had a lot of wiggle and not a lot of noise. And in this case, we've got our mean squared error, our bias, and in the orange our variance, and we're trying to find that sweet spot there of flexibility.